Hi, it's Paul Green with Biogas TV. On today's episode, we hear from Kyle Plaster from DMT. So today we're going to learn about how membrane gas upgraders work. Kyle's a chemical engineer by degree. He works for DMT out in their Western region. He's got 5 years in the business. So we're going to talk about kind of the nuts and bolts of how membrane systems operate. Hope you learned some things and enjoy the show. Kyle, how's it going?
Good, good. Thanks for having me. Appreciate it.
Yeah, great to have you along here. So let's get into it. So you've got here some help us through this a little bit. What do we have going on?
Yeah. So this is the general outlook of a membrane system. So we would handle everything after the digester. Starting with the pre-treatment. So there's a number of different things that need to happen to the gas before we enter a membrane. First would be the sulfurex, and this is handled with sulfurex and the absorption media, but this would be the removal of pollutants. So mainly VOCs, H2S, siloxanes, ammonia, all of that was removed in those beds and in the sulfurex technology. And if we want later, we can go into more detail of the sulfurex, what we offer, but really for these smaller projects and wastewater, especially, you're just needing those media beds. Also, we'll booze the gas, so get it to the correct pressure, and also do a dewatering and reheating, so getting the moisture out of the gas. Finally, we have a full compressor, so a full compression system, and that's to get to the correct pressure for the membranes. Pressure differential is really what drives the separation in the membranes for CH4 and CO2 separation. And then finally, we have just final particulate removal. And then afterwards, of course, you have different methods and different utilization of that gas. So usually it's pipeline injection, but we also see CNG and LNG these days.
All right.
So, I mean, general overview of the membrane. So we say 98% uptime, but these systems, there's really not many moving parts. Really, it's just the compressor. So we exceed that usually in most of our systems. The purity is also good. Separation of these membranes is really efficient. So we can get up to 99%, but usually, again, we usually exceed this. Low flexibility or flow flexibility, I should say. So the compressors, again, only real moving parts, so we can really get down to low flows as long as the compressor with a VFD or even a slide valve can get to those low flows. OpEx, another big benefit of the membranes is there's really no consumables other than that media for the H2S/pollutant removal and then electricity. Operation is easy, 24/7 support is going to be something that we offer, and usually that's the only thing really needed for these plants. And then really small footprint, easy to move around. So a lot of benefits with these, and really ideal for small wastewater and dairy ag projects. So how the membranes actually work. Basically, there are a bunch of small polymers put together and all the gas goes through these polymers. Certain molecules, given their permeation rate, will permeate through the membrane and actually go out or stack. And then some molecules are retained within the membrane and then actually go through the retentate. So in our system, the molecules that we're looking at mainly are CO2 and methane. If you look at the permeation rate at the bottom here, the methane is actually retained within the membrane, so it does not permeate through, and then the CO2 is retained. One topic that I think a lot of people think about with membranes is the reason why they're not super efficient at removing oxygen and nitrogen. Well, if you look down below at that permeation rate, you can see that oxygen is close to that CO2, so about half of it will go out the stack and half of it will go out the retentate with the actual methane. The problem is mainly the nitrogen. Nitrogen is so close to methane that a lot of it will be retained. And that's why an NRU at some of these landfill projects are needed with membranes. Got a little bit ahead of myself looking back up at I guess the actual separation rates. So after a first stage, you can go, usually it's around 50 or 60% methane coming into a system. After that first stage, you're looking at about 80% purity, balanced CO2. After that second stage, you can get up to 98%. Again, what I said earlier, usually you can get up a little bit higher, so 99%. And then the real difference between, say, a two-stage and a three-stage membrane system is not the purity. So you'll actually get the same purity of 99 to 99.5% in the outlet. The big difference is we have a third stage that's actually taking that that permeate from the first stage and putting it through another membrane. So we're getting that 2.5% that usually would be going out the stack, and we're saving that. So it's actually capturing more methane, and so we're not losing any revenue for these projects.
So permeate is what goes through the membrane, and retentate is what the membrane retains. So if you fed at maybe 200 psi, so the retentate is at what kind of pressure then?
So the retentate retains the pressure pretty significantly. It would be a couple psi, maybe 10 psi less. Usually we like to say if it comes in 200, to be safe, usually 180 psi coming out. What's interesting is the permeate is a pretty low pressure. It's almost ambient. It really depends on what pressure it's tied into the other side, whether it's going out to the stack or being tied in as a recycle. But usually it's down to almost 10 to 15 psi coming out of the permeate.
That's really fascinating. So if you're going onto the membrane at 200 psi, going through the membrane, you maybe only have 10 psi left. So that 190 psi is all that energy it took to get through the membrane.
That's correct. Yes. Yeah.
So on CO2, what kind of CO2 purity can you get in tail gas, and how does that tie into potential reuse opportunities for CO2?
Well, we have a methane slip of 0.2%, but of course the tail gas is going to be a little bit less volume. So usually we like to say it's never higher than 0.5% methane. And of course we're actually developing liquefied CO2 add-ons to our plants because, now everyone wants to capture the carbon dioxide for both credit use and for alternative revenue streams.
So can you comment on the difference in operating and design conditions across like the first and the second stage? So you've elevated your pressure, you're getting a lot of CO2 out of that first stage. Do you change anything like the temperature at all to get to the second stage?
I can't give exact temperatures, but I can give you an idea of what happens. So through that first stage, we know that the permeate is going to be going through a third stage. In most cases, it's going to be recycled. So we really put the temperature really high, and the high temperature will allow more gas to permeate through the membrane. So usually we're trying to get all of that CO2, and maybe we'll get a little bit more methane than we would expect, but it's okay because it's going through that third stage and being recycled. So we'll do higher temperature in the first stage and then lower temperature on the second stage, so we're not losing more methane on that second stage that's not being recycled.
So when the membrane is warmer, the pores open up a little bit. Is that how that works?
Exactly. Yep.
So kind of like things shrink when they get a little colder. The pore sizes tighten up a little bit.
Yep, that's exactly how it works.
Got it. Good. Okay. So these polymer strands we're looking at here, they're looking like a piece of spaghetti, kind of like how wide are these? Are they like a millimeter, or how wide are these fibers?
Yeah, if you look at them with the naked eye, you can barely see the hole. They're very, very, very small. And they're usually, that couple thousand of them in a single membrane.
So what are the standard sizes of these elements as far as like diameter and length of these tubes?
There's several that are offered. It really depends on, I guess, the membrane supplier you're working with. The one that we do is usually 4 to 6 inch membranes, but there's a lot on the market. And that's really all I can share, unfortunately.
And so what has DMT been seeing for membrane life in some of your field installations?
So, membrane life really has to do with that pre-treatment. If you can operate a plant and be really confident with your pre-treatment, and it doesn't even need to be, perfect H2S removal, for example. It's really just being able to monitor your H2S levels going into the membranes and just being confident. So, general rule of thumb is we say 10 years, but we have projects in the Netherlands that have been operating over 20 years on the original set of membranes.
So looking at your permeation rate, here at the bottom of this slide, water does permeate, H2S does permeate to a little bit. So H2S doesn't follow the membrane, water doesn't follow the membrane. What kind of things are really bad that could really mess up the membrane if you didn't have proper preconditioning?
Well, H2S and water can foul the membranes, but it's not, it would take a certain amount. Really, what's really detrimental is the VOCs, and those are those, big volatile organic compounds. But that's usually handled in the pollutant levels along with the H2S and ammonia.
Okay.
And then along with that, there are certain pressure and temperature requirements. So a higher pressure will, get a better, permeation, better selectivity, but there is a max because you don't want to actually blow out those membranes. And same with the heat. So there are limits as well there.
Yeah. So what are the conditions that you're trying to get to up before the membrane as far as things like dew point and pressure? What are like the optimum feed conditions you're trying to engineer to?
Yeah, so I mean, dew point, you need to get pretty much all the moisture out. Rule of thumb would be, negative 40 degrees, but I mean, it really the key here is just nothing condensing within the membranes. And when you're at a high pressure after the compressor, that can happen. So that's why we have that final compressed gas treatment where we get all the moisture out of the gas. Along with that, again, we kind of already talked about this, but all pollutants have to be out, particulates have to be out, and then the correct pressure and temperature.
What kind of compressor do you typically lean on for this service? What style?
Usually screw type, and we'll usually have a VFD, sometimes just a slide valve if it's not necessary for the project.
So that turn down that you mentioned of getting down to 20%, that's really about the VFD control? Is that what kind of limits that?
That's exactly correct. Yeah, because the membranes can handle low flows. Our system can actually close certain membranes so the flow is going, so we can have a higher flow or the same amount of flow to the membranes no matter what's coming into our system.
Yeah. Got it. So just want to go back to this graphic a little bit. So you're compressing, and so can you talk a little bit about how you just make sure with a screw compressor that runs on oil, how are you sure that you're going to get any trace oil out? You've got a final filtration step, right?
Yes. So the first thing we do is we cool it down, get all the water out, and heat it back up. We then have a series of filters. So this would be first particulate filters, and then we actually have a final carbon filter that's specifically for the oil that may be coming out of the compressor. So we do quite a lot to make sure the membranes are happy.
So cooling it drops the water vapor out, but that's too cold for the membrane. So then you're just trying to get maybe to ambient temperature before you're getting onto the membranes?
Yeah, usually rule of thumb like 90 degrees, but again, the higher, the more permeability. So it's really just what you're targeting on that first stage.
Yeah. Okay. So here's the 3-stage operations. So coming through stage 1, tell me about the vacuum blower pulling on stage 2. What does that do?
Yeah, so how the membranes work again is a pressure differential. So we might not have as high a pressure going into stage 2. So to help that pressure differential, we'll actually have a vacuum on the permeate. So the gas is more apt to permeate through. So that's just to increase that pressure differential.
So that's not so much about getting the gas back to the compressor. You're just helping the performance by pulling on the membrane a little bit.
Exactly. Yep.
Got it. Okay, so on like stage 3, then can you just walk through? So this is taking, you said the 2% methane and just getting the final bit of methane out of it.
Yeah, so this would be usually around 2% of the methane coming in roughly, for that, the flow is going to be higher. So almost like, 6 to 10% methane. And we do a very high temperature in that first stage in order to get a little bit more of that methane. And then this is the final polishing step in order to capture that lost membrane or methane coming out of the permeate. We do this because, with the IRA and different incentives, you really want to capture all that methane, just not for credit incentives, but also just because, you want more methane to put in the grid or however you're utilizing it.
But the retentate coming out of stage 3 isn't clean enough to go to pipeline, so you recirculate that back to the head of the system then.
That's correct. And that's of course the same with the stage 2 permeate.
So you only need to compress one time, and you're going through your whole system with one stage of compression.
Yeah, so we do have a fairly high recycle rate, but that's necessary to capture all the methane.
Yeah. So you have a bit of a case study we can go through here. Sounds good.
Yeah, yeah.
Tell us about the Seabreeze Farm.
Yes, so Seabreeze Farm is a facility up in British Columbia, Vancouver. It's interesting because it's half manure, but also half source separate organics. So it gives us a good mix of different feedstocks in the industry. Um, it is another thing that's interesting is there was an old water wash system here that we replaced. So it's no knock on water wash, but I think for this system, it being a small dairy farm, they realized that the best technology fitted for this product would probably be a membrane just because of the reliability. So, yep. So, like I said, they've had this project for quite a while. They had it back in 2014. They replaced it in 2020, I believe, or 2021, it says here. With our membrane system, we're able to get 99.5% methane recovery because it's a 3-stage system. Again, we claim 98% uptime, but we've actually been able to exceed this. At the time, it was only one of 5 operational plants in BC, and it supplies now 1% of BC's total natural gas. Like I said, I think the interesting thing here is the mix of feedstock. A lot of people think if you don't have enough dairy manure, then maybe you don't have a viable project. There's other ways to source feedstock, especially in this day and age.
So this says 99.5% recovery. So what would that translate into, let's say, the purity of the RNG?
I don't know on the top of my head. I mean, you of course still have a little bit of CO2. So even if you're recovering all the methane, you could have, high levels of CO2. Of course, we don't here, but I would say general rule of thumb, I think the system is running at around 99% methane purity.
Got it. So that's a pretty high flow rate. Yeah, that's a high flow rate for 275 cows. So they're taking a good chunk of offsite organic waste, it looks like.
Yes, and first it was a challenge, but we have quite a bit of analysis up front, so we're okay with feedstocks changing, levels changing. We have quite a adaptable, flexible system for different pollutants and stuff like that. There's a lot of their feedstock they're getting as fogs, so fats, oils, and greases, which can be quite can introduce a lot of pollutants.
So what does it take to run one of these systems? If I'm a dairy farmer, how do I operate my membrane system?
So it doesn't require a lot of hands-on utilization. I think the only things you have to really think about is pollutants. So of course you've got those media beds up front, and you'll need to analyze the pollutants coming out of those media beds, whether it's H2S, ammonia, VOCs, and make sure none of that's entering the membranes. So I would say monitoring pollutant levels and making sure you replace the media beds when it needs to happen. And then general maintenance, so checking filters and stuff like that. But there isn't really much hands-on maintenance, and a lot of these projects will just monitor remotely. And if an alarm goes off, we'll send someone to site, but usually it's very rare to happen.
So it sounds like membrane systems are fairly elegantly simple. I mean, the polymer chemistry, I think, is where it gets complicated, but from a day-to-day operational perspective, they're pretty simple.
Yeah, very easy to operate.
How about the compressors? You've got to just change the oil there periodically?
Yeah, I mean, the big moving part is the compressors. So we emphasize having good service and maintenance. So we have partnerships with all our compressor suppliers and local technicians. So if anything does happen, we can get on site within 24 hours and have the compressor up and running again.
Yeah, good. So how does DMT distinguish itself in the market?
I think a big thing is we do performance guarantees. So we'll really stand by our technology on purity, uptime, and even methane recovery. So that's just, how confident I guess we are in our technology is we will guarantee the performance. And On top of that, we'll do full O&M. So we'll also, based on the performance of the plant, is how we would get compensated, which I think a lot of farmers are, enticed by, because that's their payment as well.
Got it. Good. All right. Well, good stuff. So I guess just to sum up, as far as the content we're trying to get here is, how does a membrane system work? So given the proper pre-treatment, getting to those optimum design conditions that the membrane really wants to see, that three-stage approach gets you to the recovery rate you want to keep all the methane in the RNG. The tail gas can eventually get to be a recovered CO2 stream. And through understanding the conditions by which the membrane wants to flux and permeate CO2, you can really get that CO2 out of there, and through your various configurations and staging, getting the CO2 out and keeping all that methane in and complying with the RNG limits, seem to be pretty much a win all around. So, Kyle, this has been very helpful, and this is informative, good stuff. So any final things you want to share with the listeners before we call it a good call?
No, just thanks for having me. Appreciate it.
Yeah, good, Kyle. All the best. We'll see you.
Bye.